Swayam Prabha. Digital India. Educated India.
Hello everyone. We will today finish our discussion of diffusive transport. We will try to find out the expression for current in the case of diffusive transport, and then we will discuss the next important topic, that is the conductance in the case of ballistic transport and in the diffusive transport. Before going into that, let me quickly review what we were discussing. Essentially, we had this with us. We had this expression for the steady state electronic population and steady state current from the general model of transport. We could see that in the case of ballistic transport, this term is the number of modes in the device. But when we have a diffusive transport scenario in which electrons are colliding with intermediate atoms, and they may be following a zigzag motion, the electrons energy may also change in the channel during the transport. In that case, this notion of modes does not hold true, because modes are the conduction pathways, and now since the electrons are not going through unique conduction pathways, so in this case we cannot say that this quantity is the modes, and that is why this quantity is defined as the modes times a coefficient which is known as the transmission coefficient. And if we need to find out the current expression in the case of diffusive transport, we would need to find out the expression for TE essentially. And in order to find out TE, we need to find out gamma E. In order to find out gamma E, we need to find out the tau D essentially, which is the transit time in the case of diffusive transport case. You might have realized this, that we are building the transport theory from using a bottom up approach basically, because we started with the idea of density of states, Fermi function, Fermi level of contacts, and from that we are trying to build the theory of transport. We are trying to find out the expression for the currents, IV characteristics, and finally the conductance of the material. So, in the diffusive transport case, we have the electronic profile in the device which looks like this. We have axis of electrons on the left side, which is the source contact side. We have a low concentration on the drain side, and because of this concentration gradient in the device, the electrons will travel from the source side to the drain side. The profile is linear in absence of recombination generation, and we can use if the electrons follow this parabolic EK relationship, in that case the diffusion can be assumed or can be approximated by the Fick's law essentially, which looks like this. So, this will help us in finding out the tau d time, which is what we want to find out, because using Fick's law we can find out the steady state current in the device, which looks like this. So, Fick's law gives us the current density, and in a 2D channel the current density is the current per unit width, and the current will be so the total current will be the current density times the width. And from the Fick's law, this turns out to be J is essentially Q times dN. dNs by dx turns out to be delta ns 0 by L times W. And the steady state electronic population is ns 0 times delta ns 0 times W times L by 2 essentially. Okay. So, now we are in a position to directly use this expression for tau. We can essentially use tau is equal to Q times steady state electronic population divided by the steady state current. And since we are talking about the diffusive transport case, we will put a d with tau. So, this tau d will be equal to Q times this n is delta ns 0 times W L by 2 divided by I will be equal to W times J, and J is Q dN delta ns 0 divided by L. So, this is what we have in the diffusive transport case, and as you can see that delta ns 0 will cancel out, Q with Q, W with W. What is left here is this tau d will be equal to L square divided by 2 dN. So, this is the transit time, this is the characteristic time in the case of diffusive transport case. Okay. As you can see that we now need to find out we now need to know this dN parameter in order to find out the tau d parameter. Okay. This dN parameter actually comes from the scattering theory if we study the scattering of electrons in the channel by the other atoms, and in the scattering there are interaction between the electron and the other atoms, there is energy and momentum exchange, and that's sort of a separate topic to discuss about. But just with this expression at the moment, if we have a look at this term gamma pi d by 2, in the case of diffusive transport, this is Te times Me. On the left hand side, we would have gamma will be equal to h bar by tau d times pi times d by 2. On the right hand side, we have this Me. If we multiply and divide by tau b on the left side, then this can be rewritten as, let us bring the right hand side to the left side, Te times Me is equal to tau b divided by tau d times h bar by tau b times pi times d by 2. Okay. So, this is then this is the gamma in the case of ballistic transport pi d by 2. So, all this is essentially number of modes. So, this Te into Me is equal to this. So, rewriting this, Te is equal to tau b divided by tau d. So, this transmission coefficient is essentially the ratio of the transit time in the ballistic case to the transit time in diffusive case. Okay. and as we clearly know that the transit time in the ballistic case is essentially L divided by average velocity in the x direction. So, this is the expression for the transit time in ballistic case. Tau b is equal to essentially L divided by average velocity in x direction, and the transmission coefficient is the ratio of tau b to tau d. Tau d is L square divided by 2 dn, where L is the length, dn is the diffusivity or diffusion constant of the material. Okay. Now, if we put everything there in the expression for tau for Te, what we see is that Te, which is equal to tau b divided by tau d, tau b is L divided by average velocity in x direction divided by tau d is L square divided by 2 dn. Now, from the theory of scattering, which is in a way a separate topic, this coefficient, diffusion coefficient, turns out to be Vx times lambda by 2. Average velocity in x direction, positive x direction, times lambda, where this lambda is the mean free path of the electrons. So, just at the moment please assume that this is true. So, if we consider this to be the value of the diffusion constant, diffusivity, then if we put this in the this expression, the transmission coefficient turns out to be L divided by average velocity in x direction into L square divided by 2 dn. Okay. So, what is left is 2 times average velocity in x direction into lambda divided by average velocity in x direction L into 2, which comes from here. So, what is left is this. This is the case when the channel is extremely large as compared to the mean free path. So, this thing comes from the scattering theory when L is extremely large as compared to the mean free path of the electron, which means that the channel length is, or the transport is, purely diffusive transport. Okay. So, in that case this will be very less than equal to 1. When the L is extremely larger than lambda, in that case this transmission coefficient will be very less than 1. Okay. Now, this expression was for a limiting case when the L is extremely large as compared to the lambda, as compared to the mean free path. But in more general way, this expression, this transmission coefficient is written as, or can be written as, Te equals lambda divided by lambda plus L. So, this is the more general way of, more general expression for the transmission coefficient, and this holds true both for the diffusive case and the ballistic case. Okay, because in ballistic case this lambda tends to infinity, and so in let me sort of rewrite this expression for Te. So, this Te can be written as 1 by 1 plus L by lambda. In ballistic case, lambda tends to infinity, which makes this second term tend to 0. So, this means this Te is equal to 1. This is what we expect in the case of ballistic transport, but in the case of diffusive transport we have a finite lambda In the case of ballistic transport, since there is no collision in the channel, we can say that the electrons are not colliding with anybody in the channel, and that is why we say that lambda tends to infinity. So, so in the case of diffusive transport, this expression holds true, and this boils down to, or this is equal to 1 in the case of ballistic transport case. So, this is a general expression, this is true for all cases. This expression is true only for purely diffusive case, when the channel is extremely large as compared to the mean free path. Okay. So, I hope this point is clear. More generally, as a function of energy, this transmission coefficient can be written as the mean free path, which is also a function of energy, divided by lambda E plus L. Okay. So, now as you can see that we have now obtained the expression for the transmission coefficient. So, we can now easily deduce the, or we are now in a situation to find out the exact expression for the current in the case of diffusive transport. So, the expression for the current in the case of diffusive transport, as you might recall, is gamma pi d by 2 times F1 minus F2 integrated over all energy values. This was written as TE times number of modes times F1 minus F2 times dE. And now we have an expression for TE as well. Writing the expression for TE, so the current in the case of, in a general case, I would say current can be written as ME times F1 minus F2 dE. So, this is the expression for the current in the case of diffusive transport. Okay, and this is an important expression because this expression will be or can be generalized to bulk conductors as well, or we can find the bulk conductivity, the bulk IV characteristics using this expression. And as you can see that we have built from the bottom. We, like Drude's model, we did not assume that lambda is there, lambda is given. We assumed that there is a density of states of electrons in the channel. In diffusive case, electrons might be scattering. Then we had an expression for the diffusion constant. From there we obtained the expression for the transmission coefficient. We have the modes, we have the Fermi functions. Essentially the basic, the parameters from the basic physics of the device. Okay. So, this is a general expression for current in the case of devices. Okay. And as we have already seen that when L is extremely large as compared to lambda, in that case this transmission coefficient is very less than 1. When we have the ballistic case, when lambda is extremely larger than L, then the transmission coefficient is 1, tends to 1, and in the quasi ballistic case, when L is almost equal to lambda, in that case T is less than 1, but it is not very small, it is around 1, but not exactly equal to 1, because sometimes in quasi ballistic case sometimes the electron might get scattered in the channel, and sometimes they might not get scattered in the channel. Okay. So, now we in a way we have a general expression for the current which covers both ballistic and diffusive transport cases, and now we are in a situation to sort of look at another important parameter, or I would say one of the most important electrical parameter of the material, which is essentially the conductance or more generally conductivity. So, that is what we will see now. And as you might be aware that conductance is denoted by G, it is essentially the inverse of the resistance. So, if the resistance of a material is R or of a channel is R, the conductance will be 1 by R, and from the IV characteristics R is V upon I, so G will be I upon V. So, this conductance can be found out from the expression of the current, from the IV characteristics of the device. And now we are in a position to find out the IV characteristics as well, because we know the expression for the current. So, this is the general form of current in the devices, 2q by h gamma pi d by 2 f1 minus f2 dE. In more general, in other way, it can be written as Te times Me times f1 minus f2 dE into 2q by h. If we assume a near equilibrium situation, in that case we can find out f1 minus f2 in a clean way actually, because we know what is Me, we know what is Te now. This is just a constant, we just need to find out the f1 minus f2 this term, this difference term. And if you recall, f is 1, the Fermi function is 1 by 1 plus exponential E minus Ef divided by kT. So, the Fermi function is a function of energy, it can be written as a function of energy. It is also a function of Fermi levels. The Fermi function changes with energy, the Fermi function also changes if the Fermi level change. And in order to find out this difference, we need to know actually what would be the Fermi function at two contacts, at F1 at the source contact F1, and what is the Fermi function on the drain contact, and then we need to find out the difference of the two. So, just for the sake of clarity, let me again draw what we are up to here. We have a source, we have a drain. On the source side, the Fermi level is EF1. On the drain side, when we have applied a voltage, the Fermi level is EF2. The Fermi function on source side is F1, the Fermi function on the drain side is F2. The voltage that we have applied is Q times V. If the source side is grounded and on the drain side we have a battery of voltage V. Okay. So, the EF1 minus EF2 difference is Q times V. Now, this Fermi function is also a function of Fermi level, and while going from the source contact to the drain contact, what is changing is the Fermi level. So, in order to find out this difference, we will take help of Taylor series expression. So, what the Taylor series expression says that any arbitrary function can be written as in this form, factorial 1 x minus a plus 1 by factorial 2 del 2f by del x2 at x equal to evaluated at x equal to a x minus a square, and similarly there are higher order terms as well. So, this function can be approximated by this Taylor series. If we know the value of the function and the value of its derivative at a certain point, we can find out the general form of the function in this way. Okay? And if this difference, the difference or if we want to find out the function very close to point A, if the values of x are very close to point A, in that case this difference x minus A is very small. Okay. In that case, the second order and higher order terms can be ignored, because these will be very small coefficients and they will make everything to almost tend to 0. So, when x minus A is very small, in that case this function can be written as, or in very in a close vicinity of a point, the function can be, a continuous function can be approximated by this, just using the Taylor series expansion up to first order terms. Okay. So, in the case of near equilibrium transport, this EF1 and EF2 are close to each other because the applied voltage is not too much, is less. So, this QB is not a big number, it is a small number, and if we expand the Fermi function, or if we put A is equal to EF2 and x is equal to EF1, which means in this which means that we are trying to find out the Fermi function very close to EF2, okay, and in near equilibrium transport EF1 and EF2 are close to each other. In that case we can use this approximation. Okay. For that we need to know the derivative of f with respect to x, or derivative of f with respect to EF, because in this case we are assuming the Fermi function to be the function of Fermi level. Okay. So, let us try to do that. This is the, so what we can see from here is that f at EF1, if we put x equal to EF1 and a equal to EF2, is equal to f at EF2 plus del f by del EF. Let us say this EF1 and EF2 might also change, so let us not put the EF2 value here, EF1 minus EF2. Okay. So, this is f of EF1 is essentially F1, Fermi function of the source contact. This is equal to f of EF2 is Fermi function of the drain contact. This is del f by del EF times delta EF, where delta EF is the difference between the source Fermi function and the drain Fermi function. So, this is what we have, and from here F1 minus F2 is equal to del f by del EF times delta EF. Okay. And delta EF is essentially Q times V. Had the electron been a positive charge, EF1 minus EF2 had been a negative number, because in that case EF2 would have gone up. But in the case of electrons, because of an applied positive voltage on the drain side, EF2 goes down when we apply a positive voltage on the drain side. So, this delta EF is equal to Q times V. So, finally, we have obtained the difference between F1 and F2 in the case of near equilibrium transport, and that can give us the exact form of current or conductance in near equilibrium transport case. So, we have F1 minus F2 is equal to del F by delta del EF times delta EF, and if we put this in this expression, the current expression, what we obtain is I 2q by h integral dE times me into del F by del EF times delta EF into dE. And if we look at this form of the Fermi function, we can easily see from here that del F by del EF is equal to minus del F by del E. So, if we take the derivative of Fermi function with respect to E and with respect to EF, there will be only a difference of negative sign. Okay. So, we will keep in mind this fact, and delta EF is equal to delta EF is equal to Q times V. So, that is what we will put in this expression. So, let me erase this extra part. So, finally, what we have is we have I is equal to 2q by h dE into me into del F by del EF can be written as del F by minus del F by del E, and delta EF is Q times V dE. So, we can take this V out. So, I becomes, this Q also comes out, 2q square divided by h integration of dE me minus del F by del E into dE times V. So, this is the direct relationship between the current and the voltage applied across the device. And please remember that this is true when we assume the near equilibrium transport, because only in that case we can approximate F1 minus F2 by the just by the first order terms in the Taylor series expansion. Okay. So, that will that brings us to the expression for the conductance. So, the conductance of the channel is the ratio between the current and the voltage, and so this will be 2q square divided by h integration of dE me into minus del F by del E into dE. So, this is finally the expression for the conductance of the material, and we can also find out the expressions for the conductivity from this expression. So, this is what we also measure in experiments, okay? And this is a general expression, because for ballistic transport case this dE will be 1 and we will be left just with me. For the diffusive transport case, dE will be given by lambda divided by lambda plus L, and this expression will hold true. So, this expression is true for right from very small devices up to large devices. We will discuss more about this conductance in our coming class, and I would recommend all of you to go through this derivation again. This is an important concept, the conductance and conductivity of the material of the channel. See you in the next class. Thank you for your attention. See you in the next class.